This is Rosen, Discrete Mathematics and its Application, Section 2.6 on matrices. We are discussing 0-1 matrices. And a 0-1 matrix, not surprisingly, is a matrix that has only zeros or ones as admissible elements. And we will use Boolean mathematics for manipulating these elements. The term B1 or B2 will result in 1, B1 and B2 will result in 1 if both B1 and B2 are 1, otherwise it's 0. And this is the same as the concept of Boolean product from chapter 12. And then the operation B1 or B2 will give us a 1 if either B1 or B2 or 1, get a 0. Otherwise, this is the concept of Boolean sum in chapter 12. So wherever you see the AND connector, you can think of Boolean product, and wherever you see the OR connector, you can think of Boolean sum. All right, if we have a couple of 0-1 matrices, we want to find the join of them, of A and B, is another 0-1 matrix with the same dimensions as A and B. And the elements of the join will be the Boolean product, if you will, or the OR operator for the various elements of A and B. And then the meet of A and B, MEET, is also a 0-1 matrix with the result of the elements Aij and Bij, or the product of each element by element for the A and B. So the join of A and B and the meet of A and B. Let's look at an example. Here I have two 0-1 matrices. Both of them are 2 by 3, so I can calculate the join and the meet. The join, again, isn't like the OR function. You think of it as a Boolean sum in all of these cases as well. So wherever you have a 1, you're going to get a 1. So we had a 1 here, 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 here. The only place we didn't have a 1 was in the bottom right. So we're going to have a 1 everywhere except the bottom right with the join. Then with the meet, we got to have a 1 in both places, and there's only one place where there was a 1 in both places. Everywhere else will be a 0 on the meet. Okay. Now we can also take the product of 0-1 matrices, and they obey the same dimension requirements as regular matrix multiplication. The interior dimensions, the number of columns on the left matrix has to equal the number of rows on the right matrix. And we denote Boolean product as a dot with a circle around it. And just like regular matrix multiplication, the ijth element of the product matrix is a sum of products, or a conjunction, a disjunctive normal form. It's a disjunction of conjunctions. But if you have checked chapter 12, you will be able to see that this is just the Boolean sum of products. Remember, this is a plus, that's a multiply, that's a plus, that's a multiply, it's a plus. Oops, wrong way. That's a multiply plus, multiply plus, plus, multiply. Sorry about that. Okay, so find the Boolean product of A and B, where we have a 3 by 2 and a 2 by 3. These match, so the result will be a 3 by 3. And here's my build for the star. So this Cij is a sum of Boolean sum of products for the elements of the rows of A and the columns of B. All right, let's look at this. We had A and B given there, and we can see that we get a 3 by 3 matrix with for 1 here, it's going to be equal to 1 times 1 plus 0 times 0 to give a 1 there. And this 0 here, oops, will be a 1 times 0 plus 0 times 1 to give us a 0 there. Okay. And for square 0, 1 matrices, we continue to have the concept of Boolean powers. So we had powers of square matrices for regular matrices. For Boolean matrices, we have Boolean powers, and we delineate that by having this exponent with brackets around it. And we also define the zeroth Boolean power of any square matrix to be the identity matrix of the same dimension. So if we want to take this 3 by 3 matrix and find all of its Boolean powers, well, we know that a to the 0 will be the identity matrix. A to the first power is A itself. A squared would be given here. And if we want A cubed, we'll take A squared and multiply it by A. And I'll let the listener do these calculations on his own. And then A to the fourth is going to be A cubed Boolean product with A. Then A to the fifth will end up being all ones. And whenever you have all ones in Boolean, with Boolean multiplication, you're going to get all ones back. So this will be all higher power of A. And that's 0, 1 matrix operations.